got some new I got some new startup audio, like a little bit different from the electronic audio I usually use for the beginning of the stream. But anyways, we'll be just continuing the math counts road to math counts preparation. Just continue doing that. I've skipped the last two problems. The Amy 1996, I'm pretty sure. I skipped the 1996 problem and the 1986 Amy 7 and whatever the 2016 math counts national target problem, I think it was. This would look like a target problem, so I skipped those two. I didn't even know how to start them, but looking at the solution right here, it actually looks pretty straightforward if I just thought about it for a little bit longer. But I guess we'll start with permutations today. I mean, with permutations, I already know a little bit about permutations. I took counting probability class before, and you saw me doing some permutations today on a cumulus, but sadly my stream got taken down by YouTube for copyright strike by some artist. But anyways, I'll start this. Combinations are management of listening to things where orders are not important. So there will be permutations. There are 6 cards labeled 2, 3, 4, 5, 6, and 7 separately. Take out any 5 cards from the 6 cards and put them in a 5-digit number. How many different 5-digit numbers can be formed? That'll just be 6 times 5 times 4 times 3 times 2, 700. Yes, that would be the correct answer. There's combinations as well. 6, 5, 6. Example 2. There are 4 cards labeled 1, 1, 4 separately. How many 4-digit numbers can be made from those 4 cards? I learned about the stars and bars thing a long time ago, but it's going to be 4 factorial over 2 factorial times 2 factorial, which will equal 3. Well, made with 4 factorial 3 times 2. No, 3 times 2 times 2. So I do over 2 factorial, which is 3 times 2 times 3 times 2 over 2, which is 2 times 3, which is 6. And so is 6 numbers. Example 3, how many? Should I zoom this in a little bit? I don't think y'all can see what I'm doing clearly. How much can we finish to? Wow, these are long. Finish. Mage 36, 37, 10 pages. How many different ways? How many different 3-digit odd positive integers can be made using digits 3, 4, 5, 6 or so if no digit can be used more than once? How many 3-digit positive? 5 times. 4 times 3 times 2. There's just 4 fac. So 4 fac. Factorial. That's 24. 12 numbers. Let's see why. Oh, 3-digit odd positive integers. So for the last one, you could have 2 options. And with the last one, you have 2 options. Then the first number you have 3 options, and then you have 2 options. So 6 and 2, 6, 6, and 12 is 12. There's 2 factorial, 2 projections, and there's just this answer is way too big, way too big. Kinda inconvenient. So 5. How many different 3-digit positive integers can be made using the digits 1, 2, 3, 4, 5 if no digit can be used more than once? 3-digit positive, even positive integers. So for the ones place, we'll have 3 choices. For the tens place, we'll have. Oh wait, this fun. So this is 4. Okay, anyway, it works like 3 times. 4 times 3 times. 3 times 3. 3 times 2 versus 4, 3, yeah, that's gross. 9 times 4 equals 36, so no, it's 36, no, it is not 36. What was I thinking? These digits have 2 choices, so that left with 4 times 3, so 3 times 4 times 2 is 24 numbers. That is a correct answer. Tuesday. Yeah, this attitude's kind of inconvenient. Let me just check on this stream. I'll stop a little early since it's already great. Five-digit positive integers can be formed as So the tens you have 4 times 3 times. If you have four choices for the first, you can't use 0. So you have 4 choices. Then if you take 4 times 3 times 2 times 16 times 3, 16 times 6. That's 6, 3, 96 numbers. 96 is the correct answer. However, subtract 120 basic finding principles overpowered for these problems.